Hi guys, good evening.
Sir, good evening, sir.
Good evening. Let's get started.
Yes.
Yeah. So in the last class, we looked at we kind of solved, or we looked at the explicit Euler method and implicit Euler method, and also the Taylor series method and the trapezoidal method, right? I think we have seen all the four methods, and then we tried solving the problem, right? We solved it using I think we solved it using explicit Euler method and the Taylor series method, right? That's what we have done. Did we do implicit Euler and trapezoidal as well, or trapezoidal you can probably do on your own? Did we do the implicit Euler in the last lecture, or we need to do it quickly, maybe, or we can at least look at it, how it should be done? Can somebody tell me whether we have done it in the last lecture for implicit Euler? We have done, I think we have done the Taylor series, but not the implicit Euler. Okay. So what was the expression? We had dx dt equals 1 plus x square plus t cube.
Sir, we actually did it.
Oh, we did the implicit Euler also?
Yes, sir. And we
Yes, sir. Yes.
asked to check the value.
Oh, I see. Okay. Then I think you can do the trapezoidal method by yourself. Okay. It's going to be a little more involved. Okay. Fine. So any questions so far in the previous lectures or anything like that? Okay. If not, then let's move on to the order of accuracy of the trapezoidal method. So then in today's lecture, we're going to look at order of accuracy. So we said the explicit Euler and implicit Euler are essentially order h square locally, but then globally they are order h, right? But in the trapezoidal method, we have not actually formally calculated the order of accuracy. Explicit Euler, implicit Euler is straightforward to see because we have this value yi plus 1 equals yi plus h times f of xi yi plus you will have order h square, right? So that's why that is the truncation error, which is basically locally gives a second order accuracy. So today we're going to look at the order of accuracy of the trapezoidal method. Followed by that, we will look at the stability analysis for each of these methods: explicit Euler, implicit Euler, and trapezoidal, and so on. Okay. So we said essentially we are trying to calculate for some function. Let us say we have f of xi. So this is xi, and then this is xi plus 1. We have the functional values of f of xi and then f of xi plus 1, right? So that's what we have. So xi plus 1 minus xi these are separated by a value of h. Okay. Then, okay, so we said essentially the formula was yi plus 1 equals yi plus h by 2 times f of xi yi plus f of xi plus 1 yi plus 1, right? That is what the formula we have used. Of course, because f in general is a nonlinear function, then we have to linearize the trapezoidal method is what we said. But nonetheless, we don't have to do that at the moment because for the sake of calculation of order of accuracy, we can still use f of xi plus 1 yi plus 1. Okay. So otherwise, need to linearize the nonlinear function at xi plus 1 yi plus 1. Okay, fine. Okay, so then let us look at this value. So now because we said in the trapezoidal method things are going to be about the xi plus half, which is basically nothing but xi plus delta xi by 2 is your xi half. This is also equal to xi plus 1 minus delta x by 2, right? So that is what we have. So let me then expand on the right hand side what we have. That is basically f of xi yi and f of xi plus 1 yi plus 1 about xi plus half yi about xi plus half. Okay, so let me instead of taking xi, yi, xi plus 1, yi plus 1, let me work with a single variable, that is f of xi plus 1. So that's going to give me, so it means expanding f of xi about xi plus half and f of xi plus 1 also about xi plus half. Okay, so if I do this thing, what we have is f of xi equals f of xi plus half, and then I have to go, I'm expanding f of xi about xi plus half. So that means I should basically subtract off minus delta x by 2. So that means this is equal to h equals delta x, if you were to call it. And this is going to be h by 2 f prime xi plus half plus h square by 2 factorial. That means it's going to be h square by 4 times 2 factorial. It's going to be h square by 8 f double prime xi plus half plus or minus right now, right? Because this is the third term, minus h cube by 3 factorial, that is 6, 2 cube 8. So this is going to be 48 f triple prime xi plus half, and then plus h power 4 by something and so on. So that is the expansion of f of xi about f of xi plus half. Similarly, I want to expand f of xi plus 1 about f of xi plus half. This is going to be f of xi plus half. I'll go from f of xi plus 1 by adding h by 2 to reach f of xi plus 1. So this is going to be plus h by 2 f prime xi plus half plus h square by 8 f double prime xi plus half plus h cube by 48 f triple prime xi plus half and so on. Okay, that is what I have. Okay, now let me add these two things. So because we have something similar here, so what we have is f of xi yi and f of xi plus 1. So let me add these two. That's going to give me f of xi plus f of xi plus 1 is going to give me 2 times f of xi plus half, and then this term gets cancelled, right? So this basically gets cancelled, and then what I have is plus h square by 4, right? I have 2 halves here, times f double prime xi plus half. Then this term gets cancelled, and then what we end up with is plus order h power 4. Okay, that is the term which will basically be coming here. Okay, so this is what I have. But then what I have in this expression is basically f of xi plus f of xi plus 1 divided by 2, right, into h. So this is the term I have. So what I'm going to do is I'm going to write, if I can write this thing, yeah. So essentially my f of xi plus f of xi plus 1 by 2 is nothing but f of xi plus half plus h square by 4 f double prime xi plus half. Okay, that means if I were to write f of xi plus half equals f of xi plus f of xi plus 1 divided by 2 plus h square by 4 f double prime xi plus half. Okay, that means if I were to multiply this with h, it's going to be h times f of I plus half xi plus 1 equals h by 2 times f of xi plus f of xi plus 1 plus this is going to be h cube by 4 f double prime f of xi plus half. Okay, that means if I want to calculate this integral, that is xi to xi plus 1 f of x dx, right? I could write it as this one, or if I assume that essentially this is nothing but, if I consider this as a constant value at this centroid, that is going to be f of x I plus half times delta x, that is nothing but xi plus 1 minus xi, that is nothing but h times f of xi plus half, right? So that's what I have. So if I say that essentially this is an approximation for this, which we are replacing with these terms, right? We are replacing with these terms, and then in the formula we only have up to here, right? We only are approximating it as h by 2 times f of xi plus f of xi plus 1. So The truncation error that is involved is order h cube. Okay, so when we say that this is equal to, when we say that this is equal to h by 2 times f of xi plus f of xi plus 1 plus order h cube. Okay, so what we have here is that the trapezoidal method is locally third order accurate and globally second order accurate. Okay, so that is about the order of accuracy for the trapezoidal method. Okay, fine. So then let's move on to the we have seen stability analysis in the context of the finite difference basics of finite difference method. So we have to deal with again the stability analysis as well as and order of accuracy. Okay, even in the context of these methods. Okay, we have already shown the order of accuracy, so I'll kind of come back to this a little later. So let's look at the stability analysis of the different methods. Okay. So what was stability analysis? So stability analysis is basically we want to know whether our errors or our solution, right, will be bounded or will it grow from step to step. Okay, so so we have again written out different things. So what were essentially the equation we are trying to solve is dy by dx equals f of xy. We will also use, let us say, dy by dt equals f of y comma t or t comma y. So this is going to be f of t comma y. Okay, let us say we work with this equation in which t is the independent variable, y is the dependent variable. And then we need to have some kind of a model function. We need to have a model function with which we can decide on the stability of the scheme. So we need to have a model function using which the stability of the scheme can be decided. Okay, we have seen that in this context, a particular scheme can be stable, right? Stable numerical scheme. That means it is unconditionally stable. And then similarly, we have something known as an unstable scheme, or we have also identified something that is known as conditional stability, that is conditionally stable scheme. Right, so we have these three choices. One is stable scheme, unstable scheme, and conditionally stable scheme. So we want to apply this particular stability analysis to the explicit Euler method, explicit Euler, implicit Euler, and then the trapezoidal methods in the context of solving ordinary differential equations. And to be specific, we are going to look at essentially the first order ODE. Okay, but then the idea is now, as we said, in the context of finite difference equation, we can only apply it for simple linear equations, right? We said you cannot apply stability analysis to complicated multidimensional nonlinear equations. However, the insights gained from simple linear equations are useful in guiding us in what will be the delta t for complex, more nonlinear equations and so on. So that is the idea. So the idea remains the same in the context of ODEs also. Here also we're going to apply the stability analysis to a model equation. Now we want to derive a model equation, okay, that is going to retain the essential elements such that the stability of the method can be identified. Okay. Now, we have taken this route of using the round of error as the argument to come up with, whether the round of errors are growing or decaying and so on. In the context of ODEs, we don't have to take the round of error route. Of course, we can certainly take it, but then it appears from the solution itself, we can say whether the solution is growing or not growing. Okay, so as a result, we don't have to invoke this solution on infinite precision computer, solution on finite precision computer, and then take a difference of these two and then come up with an equation for the round of error and then look at how the round of error is growing or not growing. So all those things we don't have to do. But however, we can think of the equations being done in that way because there is a round of error always that is associated, which are giving rise to the growth of the solution. But in this case, the solution itself will grow or decay. Okay, so that means we need to come up with a model function. Okay, because we cannot apply it for each and every function that we get. So as a result, we want to come up with a model function. So let me take dy dt equals f of t comma y, but then now I have to change this t comma y to be a model function that will capture the essential features or essential elements such that this method can be applied or commented upon to several other functions. Okay, so let me expand f of ty about t0 comma y0, okay, because in general f of ty is a nonlinear function. Because it is a nonlinear function, so we're going to expand this about t0 comma y0. So essentially we're going to use the two-dimensional Taylor series expansion, okay, and then going to expand. So that means what would be f of ty? F of ty is going to be f of t0 comma y0 plus, in case of xi and xi plus half, we have written xi plus half minus xi, that is h by 2. So in here I have t and t0, so I can write this as t minus t0 partial f by partial t evaluated at t0 comma y0, okay, then plus I have y minus y0, then we have partial f by partial y evaluate t0 comma y0, okay, plus I'll have, so these are the h by 2 or t by 2 terms. Then we also have plus t minus t0 square by 2 factorial dou square f by dou t square evaluate t0 y0, plus we have 2 times t minus t0 y minus y0 times dou square f by dou f dou t evaluated at dou y dou t dou square f by dou y dou t evaluate t0 y0, plus we have I don't have to do t minus t0 square, I think divided by 2, I don't have to write probably. This will already come to be, so I should say 1 by 2 factorial times this, okay, that is better. And then plus I will have y minus y0 square dou square f by dou y square t0 y0, and then plus we will have the third order terms and so on. Okay, so that is how I can expand f of ty. So this is straightforward. It was there if it was only just expansion about one single term, that is about t0, we would have only had these terms, right? We would have only had this term, this term, this term, and so on, right? But then because now it is a two-dimensional expansion about both t0 and y0, we have these remaining terms that are there. Okay, fine. So then now what we say is that, again, just like in the context of the basics of finite difference method, we cannot deal with the nonlinearities that we have if we keep them. So as a result, we're going to neglect all the non-linear terms. Okay, so that means we're going to only deal with linear terms in the model equation. Okay, again, this is because if we keep the nonlinear terms, we cannot really analyze them by hand, and the stability characteristics cannot be found. However, if we get a nonlinear problem in reality, we're going to anyway linearize it and then use the linearized system of equations. So eventually we're going to come back to a linear system which is coming from a nonlinear system. So as a result, we don't have to include the nonlinear terms. So we're going to only include the linear terms. So if I include only the linear terms, and I can write f of ty equals, I have these three terms. I mean, these actually 5 terms, right? Because I'll get 2 terms from here, 2 terms from here, and then this is 1 term, which I'm going to write here again. F of t comma y equals f of t naught comma y naught minus, if I go up, what we have is minus t naught dou f by dou t at t naught comma y naught, and then minus y naught dou f by dou y at t naught comma y naught, and then plus I have t times partial f by partial t at t naught comma y naught plus y times partial f by partial y at t naught comma y naught, right? That's what I have. Okay, so that's what we have. Then essentially I can write this as, because this is a constant, right? This is already known. I'm evaluating a function at t naught comma y naught. Similarly, partial f partial t at t naught y naught comma is a constant, and then t naught itself is a constant, and then y naught is a constant, and partial f partial y evaluated at t naught comma y naught is also a constant, right? So as a result, all these things are constant. So we can write f of ty, which is the right hand side in the model equation, equals some alpha 1, that is a constant, plus again this is another constant multiplied with t. So this is going to be alpha 2 times t. Okay, plus I have, this is again partial f by partial y is a constant. Let me call that constant lambda, and then I'm going to write lambda times y. Okay, so I can simplify my right hand side of the model equation to be some alpha 1 plus, which is a constant. So where alpha 1, alpha 2 and lambda are constants. Okay, these are all constants. And then so this is the model equation I want to work with. So this is the model equation. But then what we see is that if I'm going to still further neglect the inhomogeneous part to simplify the analysis, inhomogeneous part is neglected to simplify the analysis. That is one part. The other part is the last term, lambda y, is the most dangerous term, right? Why do we say that? So that means if I neglect alpha 1, alpha 2 t, then I can write f of ty equals lambda y. Okay, we say that we need to include this term because this is the most dangerous term in the formulation. Okay, why is this the most dangerous term? If you go back, what we have is dy by dt equals f of t comma y, right? And then we have expanded this f of ty about f of t naught y naught, and then we have done several terms, neglected all the second order terms. We ended up with the first order terms, linear terms, and then within the linear terms also we have neglected alpha 1, alpha 2 t, and then we said only lambda y I want to keep. That is because if lambda y is included, then this is going to be, if I were to write dy dt equals lambda y, then I can, if I were to find an analytical solution to this, this is going to be dy by y equals lambda times dt. So if I want to integrate this, I'm going to get ln y plus some ln c equals lambda times t. That means I'm going to get y times c equals e to the power lambda t, right? Which is basically nothing but as t increases, okay, what will happen to the solution? It is lambda t. If lambda is positive, the solution y is going to grow. Okay, that means if with t increases, if it is going to grow, then it can grow unbounded, and then it can grow exponentially, right? So that is why this is the most dangerous term. But instead, if I were to keep only the, let us say the dy dt equals alpha 1, then this is going to be simply integral dy equals integral alpha dt. So this is going to be simply y plus c equals alpha t plus alpha t, right? So this is basically just a linearly, increasing solution, which is not that of a problem. Similarly, if I had kept only, let us say, the second term, that is alpha to t, then this is going to be similarly dy equals alpha to d dt. If I were to integrate, I'm going to get y equals alpha to b squared by 2 plus c. This is only basically going to give me quadratic increase with respect to t, which is not that of a problem. Whereas the growth of this one is problematic because it is growing with respect to exponentially with respect to time. Okay, so that's why we're not going to consider the effect of the first two terms, that is the inhomogeneous terms. We call it inhomogeneous because at y equal to 0, the right hand side goes to 0. If it is, at t equal to 0, when I said y equal to 0, essentially this goes to 0, whereas this doesn't go to 0. Okay, so as a result, we call this term as inhomogeneous. However, essentially what happens is the stability characteristics, the stability characteristics are not affected by neglecting the inhomogeneous terms. Okay, so as a result, the stability characteristics are not affected, so that's why we could kind of neglect them. Okay, so that means now we want to deal with our model equation. So we said dy dt equals f of ty, and then we said this f of ty is now equal to lambda times y. Okay, so that is our model problem that we want to solve. Okay, fine. Questions so far? Any questions? So what in terms of what we're doing? I'll just switch off my power off. Yeah. So any questions so far? What we're trying to do? Okay, fine. So let's look at then. Yeah.
No, sir. Things are okay. We should proceed for this actually.
Okay. Okay.
Basically,
fine.
we have to again go back to the your notes again and then come back to you.
Sure. Yeah, no problem. Okay. So we are dealing with a model problem, that is dy equals lambda y. Okay. Now let us try to apply the explicit Euler method. Explicit Euler method. So in the explicit Euler method, what do? We say that if dy dt equals f of dy, explicit Euler method says yi plus 1 equals yi plus, this is going to be some h, right, times f of ti comma yi, where h is the time step. H is the time step of the problem. Okay, so yi plus 1 equals yi plus h times f of yti. Okay, that means in this case yi plus 1 will be equal to yi plus h is this time step, and the right hand side is lambda times yi. Okay, so what I have is yi plus 1 equals yi plus h times lambda y. That means I can write this as yi times 1 plus lambda h. This is yi plus 1. Okay, fine. This is okay. But then the thing is that now this lambda y we have, so we can actually let lambda to be complex. Okay, it need not be restricted to simple values. It can be a complex number as well. Okay, so as a result, we can write lambda as lambda real part plus I times lambda I. So in certain problems, we will get lambda to be complex as well. Instead of a real number. So we can actually allow lambda to be complex. Okay, so what does it mean? If lambda is complex, what we have is dy dt equals lambda y. Okay, we said the solution to this problem is the exact analytical solution to this problem is y equals e to the power, or we can say c e to the power lambda t, right? That is the solution, right? Y, or I have written previously as some yc equals e to the power lambda t. The c can be brought to the right hand side. So this is y equals c times e to the power lambda t. That is the exact analytical solution. If lambda is allowed to be complex, then what will happen? Then y equals c e to the power lambda r plus I lambda I times t. Okay. Then we can write this as c times e to the power lambda r times t times e to the power I lambda I t. Okay, because it is addition in the exponential, I can write it as a product of two exponentials, right? Then if I take e common, then I have lambda r plus I lambda I plus times t. Okay, so that's what we have. Okay, now I want to know what is the role of lambda r and lambda I. So this is basically the real part. That is the imaginary part. What is the role of real part and what is the role of the imaginary part in the solution? So I have now, this is the exact analytical solution I have obtained. Now what we say is that if we fix lambda r to be some value, let us say lambda r is greater than or equal to 0, then how will this term behave? Let us say c is some constant. So e to the power lambda r times t. If lambda r is positive, then this component of the solution is going to grow with time, right? Because it's going to go as e to the power some positive times constant. If lambda r is less than or equal to 0, then e to the power lambda rt is going to decay with time. Okay, but then we will not have any ordinary differential equations or anything where things grow exponentially with time, right? Because if things grow exponentially with time, what will be the final solution that you would get? If things are growing exponentially with time, the final solution you will get basically will be infinite. So no physical process will be there which actually have a solution that is growing infinitely with time, right? So as a result, we will not be interested in values of lambda r being positive. So we are only interested in then, this case is ruled out. Then we are only interested in cases where lambda r is less than or equal to 0. Then this is going to be e to the power lambda rt, where things decay with time. So this is possible. This is possible in physical applications. So if I'm going to consider, let us say, only the real part, I want to keep this on hold for some time. How will the solution going to look like? So then what we have is we have y equals c times e to the power lambda rt. Okay, and we said this is a constant and a negative value. So if I were to plot what is this solution is going to be essentially, it is, let us say, on the x-axis you have time, on the y-axis you have y, some constant times e to the power lambda rt, where t equal to 0 you have some value. So this is your constant. Okay, and then it is going to decay exponentially, right? So that's what we are going to have. So that's going to decay exponentially with time. Okay, and then I can also draw another imaginary curve, which is basically a reflection of this. Okay, that is what I have. So this is the solution for, let us say, for equation 1. So this is the solution for equation 1. That means this is how the I've kind of not drawn it so nicely. It's not linear actually. Let me draw it slightly better. Okay, let me draw it slightly better. So it's kind of decaying exponentially. Okay, I think that is better. And then it's decaying. So this is the solution of the first part of the solution. Okay, it's going to define your amplitude, right? The amplitude is decaying like this. That is what it's going to define. Now, what is the so this basically defines your amplitude. Okay, what is the effect of the e power I lambda it on the solution? So if it is e to the power I lambda it, then what we have is we have something like e to the power I lambda it. If I'm going to call lambda it as theta, then we have what is e to the power I theta. So this is going to be cosine theta plus I sine theta. That means it's going to be cosine of lambda it plus I sine lambda it, right? That is what I have. Okay. What will be the, so what is this quantity? this quantity is basically what will be the amplitude of this? Amplitude of this is basically 1, right? It has an amplitude 1 because this is going to be square root of cosine square theta plus sine square theta. That is, amplitude is 1, or it is being multiplied with 1. Okay, and then what is the what will be the how will this look like in the as theta is increasing? That means as time is increasing, how is this e to the power I theta going to look like? Right, e to the power I lambda it is going to look like essentially, if I'm only plotting e to the power I lambda it, then it's going to look like, so this is the time, then it's going to look like essentially some solution like this, which is basically your e to the power I lambda it. Okay, now this has an amplitude of 1. Okay, it goes to +1 to -1. Okay, on this one I have some component y2. Okay, let's call this as y1. Okay, so this is how it's going to look like. It's basically going to define your oscillatory solution. Okay, but it is not going to define the amplitude. The amplitude is fixed at 1, but the solution is going to go between that amplitude of +1 -1 as time is progressing. That means you have an oscillator solution. Now, if you are considering a solution that is a component, or if it is a product of these two, that means e to the power lambda RT times e to the power I lambda IT times some constant C, that is the full solution we are obtaining. Then this is being multiplied with this amplitude, right? That means the amplitude is now decaying with time. So essentially the final effect is that the product of these two is basically going to be like this, right? So essentially the amplitude is decaying, whereas the oscillator solution is also there. So that means your solution is going to look like something like that, right? It's going to decay like this. So that means its amplitude is being constrained by the first term. That means the real part, lambda RT, is responsible for the amplitude. Okay, and the lambda I lambda IT is responsible for the phase, we can say, or is basically responsible for the oscillatory solution. Okay, so we can either call the amplitude and the phase. Okay, that means the amplitude is always dictated by the real part. I think that we should keep in mind. Okay, the imaginary part, whatever value we get for lambda, it's only going to define the phase. Okay, that means it is going to be between +1 to -1, or it is going to be between plus e to the power lambda RT and or e to the power lambda RT when it goes, and minus of that, right? It's going to basically go between those two values. Okay, because it is being scaled by multiplied by with that constant. Okay, so that's what we should remember. So this is the behavior for the exact solution. Now, what we said is that we are interested in only solutions that decay with time. So as a result, our lambda r is less than or equal to 0. Okay, so we are only interested in problems which have lambda r less than or equal to 0. Right? Otherwise, we are not interested, because there are no such problems where we are not in a solution where the final solution is infinite, right? So that's why lambda r is less than or equal to 0 is what we are interested in. And then it can take any lambda I value, right? We are really not worried about lambda I, because lambda I is going to define only the phase. That means I lambda I t is going to only define the phase of the solution, or the oscillatory part of the solution. So as a result, in the exact problem that we want to solve, where we want to write dy by dt equals lambda times y, we want to write it as lambda r plus I times lambda I times y. Okay, but then we are interested in only values of lambda r less than or equal to 0, and then any lambda I. Okay, so when we let it to be complex, then we want the real part of this complex number to be less than or equal to 0, and then any lambda I can be taken in the problem. So this is our model problem which we want to solve. Okay, that means if I were to plot, let us say, this real and imaginary parts of lambda. Okay, that means let's say this is the real part of lambda r. Okay, and then this is the imaginary part of lambda, that is lambda I. Okay, let me call this as lambda r, or this is the real part of lambda, and then imaginary part of lambda or lambda I. Okay, that means our solution space is essentially this entire space, right? We are saying lambda r is less than or equal to 0. So this is your 0, 0. So lambda r goes on the x-axis, lambda y goes on the y-axis. So this entire space where it is from 0, 0 to the entire left, right? Lambda r can be negative and lambda I can be anything in the y direction. So this is our solution space, or solution space in a sense. The model function can be picked up from anywhere in this domain, but not anywhere from this domain, because this is going to give us growing solutions, which we are not interested in. Okay, so that is the idea here. Okay, then in this context, let's go back. We have written yi plus 1 equals yi times 1 plus lambda h, right? If we go back to the explicit Euler method, what we have written is yi plus 1 plus lambda h. Now that we are using I for the complex number, for the imaginary number as well, let us rename to n instead of I plus 1. So that's going to call it as yn plus 1 equals yn times 1 plus lambda h. Okay, because we are using, because I is reserved for I, we have been using for the complex number. Okay, that which is basically equal to square root of -1. Okay, so then if this is the case, I can write my, if I take n equal to 0, I can write y1 equals y0 times 1 plus lambda h. Okay, similarly, I can write y2 equals y1 times 1 plus lambda h. But then I know that y1 is basically equal to y0 times 1 plus lambda h. So I can write this as y0 times 1 plus lambda h times 1 plus lambda h. Then I can write y2 equals y0 times 1 plus lambda h whole square. If I follow the same recurrence, then I can write yn equals y0 times 1 plus lambda h to the power n. Okay, so this is what I have. Then either we, in terms of solution or in terms of the round off error that we have discussed, for yn to be, for this method to be stable, we want this quantity, whatever is there, right? If we were to call it as sigma, we want this sigma to be less than or equal to 1. Okay, only then yn by y0 will be bounded, right? So we don't want yn to be growing, right? So as a result, we want the sigma to be less than or equal to 1. What is sigma? Sigma is nothing but 1 plus lambda r h. Okay, 1 plus lambda h. That means we want 1 plus lambda h modulus to be less than or equal to 1 to obtain a stable solution, right? Otherwise, yn will grow with respect to time, right? As n grows, and then it is going to be, if it is more than 1, it is going to be increase. It will increase, and eventually it will become infinite. Okay, so now because of the simplicity, we are able to see this for the solution itself. Otherwise, we can think of it like also as the round off error being growing at every step as such. Okay. Now, 1 plus lambda h modulus is less than or equal to 1. What is this condition? This condition is we have obtained for the explicit Euler method. Okay, but then I can also write this as 1 plus lambda r h. Sorry, 1 plus lambda r h plus I lambda I h modulus is less than or equal to 1. Okay, what is the modulus of the complex number? That is its magnitude. So we can write this as 1 plus lambda r h whole square plus lambda I h whole square to be less than or equal to 1. Okay, that's what we have. What is this condition? This condition is basically, if I were to deal with lambda r h as some x, lambda I h as some y coordinate, this is basically nothing but lambda r h minus of -1 square plus lambda I h lambda I h minus 0 whole square less than or equal to 1 square. Okay, so then what I have is x minus a square plus y minus b square less than or equal to 1 square. Okay, what is this? This is basically the equation of a circle with center at a comma b and radius of 1. Okay, That means what is the center? Center is -1, 0. So that is the center of my circle. And then radius equal to 1. So what does it mean? That means what we have is, so for all values of, okay. Okay, so then I can draw from here. Oh, I should draw. Okay, probably from here. Okay, that's what I have. Hopefully, okay, this guy. Okay, so fine. So this is what I have. So this is my okay. 1 second. So this is my real axis. Real axis is basically lambda r times h. The y-axis I have chosen to be lambda I times h, right? That is what my x and y are, right? X is lambda r h, lambda y which is y. On this diagram, I have this circle. This circle whose center is at -1, 0, and this is 0, 0. This is -2, 0, because the radius is now 1. So you go from -1 by 1 more unit, that is -2. Okay, so this is the circle, and then everything inside this circle is now, this is less than or equal to 1, is the stable region, right? That means you can now connect this with the exact solution. In the exact solution, what we said that when we had the lambda r h, or lambda r and lambda I, we said everything, the entire negative axis is our stable solution, right? Whereas you can see that, so this is for the exact analytical solution. That means you are able to find exact solution if your lambda r is less than or equal to 0, irrespective of whatever is the lambda I. But when you want to apply explicit Euler method, then you realize that you can only apply explicit Euler method if your delta r times h, or lambda times h only satisfies this condition, which means that only if your lambda times h is inside this circle, only inside this circle, you're going to get stable solution. That means your lambda is fixed by your problem, right? You are given dy by dt equals lambda y. So lambda is already fixed by the problem. Then what is the h you should take? You should take h such that it falls, that lambda times y or lambda times h falls within this circle. If it's not going to fall within the circle, then your solution that you would get for the using the Euler method is going to grow unbounded, right? It is going to diverge. Okay, so that is the idea now. So you want to keep your lambda r times h to be falling within the circle. So adjust h such that this condition is satisfied. Okay, so that is the stability result for the explicit Euler method. Now, of course, now we can analyze a few more cases. So the cases are, let us say if I have only real lambda, that means lambda r is less than or equal to 0, and then lambda I is equal to 0. Okay, so that is what I have. If lambda r is equal to less than or equal to 0 and lambda I equal to 0, if lambda is equal to 0, what will happen? I am on the x-axis, right? Because I can only take my lambda I is 0, so I can be anywhere on the x-axis. That means I can be anywhere on this x-axis, but then I cannot take anything more than 2. So for that reason, my lambda r times h modulus should be less than or equal to 2, right? It cannot be more than that. So as a result, the maximum time step I can take would be 2 by modulus of lambda r. So this is the maximum time step that can be taken for obtaining stable solution for a given lambda r when lambda I is equal to 0. That means if you have purely real values of lambda, the maximum time step you can take is basically h is less than or equal to 2 by lambda r. Okay, so this is the stability condition for explicit Euler method, but it is only valid for lambda r positive, lambda I is equal to 0. Okay, otherwise we have seen that modulus of lambda times h equal to less than or equal to 1. Okay, so that is the first thing we can look at. We can also look at essentially this circle. We can note that the circle is basically only a tangent to the y-axis, right? The circle is not touching the y-axis, it's only a tangent. That means the more you're going to go closer to the origin, the more it will be a tangent, right? It will never touch the y-axis. It's only going to pass through 0, 0, but it is going to not touch it until you go to pass 0, 0. So if you are going to go to 0.001 and 0.00001 and so on, it is still going to be a circle, right? It is going to be smaller and smaller. That means the circle is only a tangent to the y-axis. What does it mean? That means if you're going to take purely imaginary values of lambda, that means if your lambda are equal to 0 and then lambda I is not equal to 0, right? If you're taking purely imaginary values of y, then this is never going to be inside the circle, right? Because it is only a tangent. So the y-axis is not going to be inside the circle, right? If you take any values on the y-axis, they are not going to be anywhere except for 0, 0, right? Only 0, 0 is the one which is going to be inside the circle. Everything else is going to be outside. That means it is not stable. So explicit Euler is not stable for any lambda I if lambda r is equal to 0. Okay, so so that means for purely imaginary values of lambda, we cannot apply explicit Euler method and then obtain a solution. Okay, so that is the idea. Similarly, if we have, let us say, a purely real value, okay, if I have a purely real value, then my solution is basically 1 plus lambda h modulus is less than or equal to 1. Okay, if I have purely real lambda, right, then I know that if this is purely real, for this to be less than or equal to 1, I know that the because purely real and then lambda r is less than 0, right? This is less than 0. So as a result, 1 plus lambda r h is less than or equal to 1, and then lambda r is negative. When can this condition be satisfied? This can be only satisfied, right, when my when the magnitude of lambda r h is negative, right? When this is when the lambda r h is actually negative, right, and then but the magnitude of this one is less than or equal to 1, right? Only then this condition can be satisfied. So what this means is that my 1 plus lambda r h is negative, right? Or yeah, so this is basically negative, and the magnitude of lambda r h is greater than 1, right? That means the magnitude of lambda r h is greater than 1, and then lambda 1 plus lambda r h is basically negative. Only then this can be or magnitude of this is greater than 1, and this entire thing has to be smaller than 1, right? Only then this is basically satisfied, but for that this has to be negative. Okay, I think I'll stop here. We'll come back to this discussion tomorrow again from here so that it will be clear. Okay, if you have any questions, you can ask me. Otherwise, we're going to stop it here, folks.
Sir.
Yeah.
Yeah. So while deriving this model function, we had three terms like alpha 1, alpha 2t, and lambda y. So alpha 1 and alpha 2 were neglected, considering that lambda is the major contributor to the equation.
Stability, correct.
Stability. So, but now it comes out that lambda is very limited at the end of the discussion. So, in that case, whether that alpha 1 and alpha 2 are still going to affect our results?
Yeah, so essentially, yeah, no, the toughest part in terms of stability is with respect to lambda y actually, right? Because if you take the what do you say? If you take the alpha 1, alpha 2, your solution is linear. So this is not very difficult to solve, right? So if you are going to get a PDE, or if you're going to get an ODE, which is like dy dt equals alpha 1, or you're going to get dy dt equals alpha 2t, then integrating solution is not difficult. I mean, you don't even have to apply numerical method. You can directly solve for it, right? The only problem comes when you have on the right-hand side, if you have function of y, right? Because function of t is very easy to do. You can just integrate it. So the stability is not a problem for these kind of problems, for these kind of right-hand sides. Only when your problem involves some function of y, that is when the solution becomes much more complicated. So that is the reason we are not really worried about solving with alpha 1 and alpha 2. Right? Because you can simply write it as, essentially y goes as quadratic, then you essentially get a solution. This can be easily, integrated. So not a problem. Just 1 second. Hello? Yeah, so that is the reason why we have neglected or we have not considered the contribution of the first 2 terms.
Sure, sir. Thank you.
Yeah.
Sir, I have a request to make, sir. If you allow, can I just proceed, sir, please?
Sure, yeah, please.
I'm sorry, sir. We are not able to ask you many questions regarding concepts clarification because still we are going through your notes and probably one of the class probably if we request you to just dedicate for clarification of concept, that will be great.
Yeah, sure. No
that
problem.
is request number 1, sir. And second request, sir, at the end of every chapter, what I mean to say is that if you can just summarize what I mean to say is the concepts that you have taught, because at times what happens, sir, is basically this subject is quite interesting and very useful for us because we go through a lot of CA simulations and we look at the results.
Yeah.
But the volume of the subject is so high that probably it is what I mean to say difficult to what I mean to say is understand and keep in the mind. So,
correct. Yeah, even getting a full picture of what is we've done.
Exactly, sir. So that will be great.
Sure.
And third and last request from my side, sir, or our batch side, sir, is basically it's little I would say selfish request from our side, but still we want to make it. It's your own discretion, sir, if you can consider or not. Sir, if you can just indicate what I mean to say is as far as I counted, almost 23 derivations are there, what you have taught so far. And, so, sir, a few of them, which is a probable questionnaire exam, so that will help us to what I mean to say concentrate and
right. Okay.
prepare ourselves in a better way because it's a request, sir. You can consider it, sir, if it is possible, sir. It's just a simple request to you, sir.
No, see, I mean, I would say you are already solving the assignment problems, right? So that should give you enough help towards the preparing for the exam,
Yeah, from numerical point of view, sir, but derivation point of view, I just wanted
so derivation point of view, I don't think it is too difficult. See, derivations also, if you know the starting point and how it proceeds, we should be able to derive it. I mean, what I suggest is maybe you take a look at what we have derived, then it is not too difficult. You can kind of, close the notes and then try deriving by your own, what we have done.
I can find a symmetricity in all the derivation that you have shown, sir. But sometimes it becomes very difficult to keep all the steps in the mind.
Correct. I'll do one thing. Maybe what I'll do is we'll have some kind of a practice problems. Okay.
Yes,
for the exam. Okay. So that I will discuss this. I will probably come up with, let's say, 2-3 problems, which we will discuss in the class. I will ask you how you will solve it. And then what you can do is, I may not give you a solution, but you can go back and try solving them. So this should basically get you prepared for the exam. Basically you solve this thing. Although you're solving the assignment, I think it is better if you have some kind of practice problem for the exam, some preparation for the exam. Okay. So you can expect similar things in the exam, so something like that. It may not be the same. It may not be the same numerical method, but then once you practice, you'll be at a better in the exams. Okay, maybe you'll do that. So we'll set out a separate class for clarification whenever you want. You let me know. Otherwise, in every class also we can dedicate some 50 minutes, 15 minutes or 20 minutes for the clarification if anybody has. That's not a problem. It can be from any chapter, not an issue.
Thank you so much,
Towards
sir.
the end or something, and then we can also summarize the chapter. That's not a problem. Okay.
Thank you so much.
And I'm also supposed to post you the tutorial which I forgot. I mean, assignment problem. I'll probably post it today or tomorrow. Your next assignment on the basics of finite difference method.
Right. Sir.
Yeah. Okay. All right.
So thank you so much, sir. Thank you so much.
Yeah. No problem. Thank you. Okay, guys. If there are no other questions, we'll call it a day, and then talk to you guys tomorrow. Okay. At 4 o'clock.
Thank you, sir.
Thank you.
Thank you,
Bye.
sir.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you.